In the previous lecture, we learned about perceptron, and also we learned about the structure of feed-forward neural network. Feed-forward neural network is layers of perceptron. We learned how to train perceptron, and we wanted to learn how to train feed-forward neural network in this lecture. So the algorithm that we are going to study is called backpropagation. It's dominant algorithm for training feed-forward neural network. As a reminder, feed-forward neural network had this structure. You know, you have a d-dimensional. When you have d-dimensional data point, then you have, you know, a layer of perceptron, and each perceptron will be fed by these inputs, and there are some weights here. So these inputs will be weighted, and then we have weighted sum of these inputs. A nonlinear function will be applied to the weighted sum of this input, and we're going to have an output. But this output is going to another layer of perceptron. And we could have many layers. And eventually we have the output layer. And output layer could be only one node, could be multiple nodes. So say, for example, for simplicity, assume that there's a one node, and you have a y hat here as the input of this network. So we would like to train it. By train it, I mean that, you know, originally, if I had n data point, I would like to minimize y minus y hat. So if I write it in a vector form, so each of them is a vector of length n. So for n data point, I have this, and I need to minimize this. So basically, I need to learn these weights in a way that this objective function is minimum. Okay? So if we follow the procedure that we had for basically any other algorithm that we study in this course, I need to take derivative of this objective function with respect to the parameters that I would like to optimize, which is the weight. So basically, I have to take derivative of this with this weight, with this weight, with this weight, with this weight. With all of these weights are parameters of this model. If I change them, the output will change. And I would like to know which set of parameters are optimum set. So I have to be able to take derivative of this objective function with respect to these weights, and then either set it to 0 if there is closed form, or do gradient descent, or take the second derivative, do you know, Newton method or something like that, so a numerical method. So anyway, I need to take this derivative. Okay. And backpropagation, the algorithm that we are going to study today, is basically a way to take this derivative. So we are going to learn about backpropagation. Okay. So let me I'm just going to consider a snapshot of this network, a part of layers and nodes, and then we'll see that how we can compute this derivative. So I'm going to consider so this is layer L, this is layer I, and this is layer J. There are many nodes in this layer, and there are many nodes in this layer, and there are many nodes in this layer, but I just pick one node for each layer. And there are weights, there are edges between these nodes, and there's weight associated to each of them. So UIL is one weight, and UJI is another weight. And don't forget that these are perceptron. So basically, each of them take the input and sum them, add them up. So basically, I divide each perceptron to two parts. The first part would be a weighted sum of the input. And the second part is when we apply this nonlinear function. In the perceptron, we had a sine function applied to weighted sum, right? So there's a nonlinear function which has been applied to this input. So I divide each of these to two parts. So this is AI, this is ZI, this is AJ, and this is ZJ. And this is AL, and this is ZL. And basically, AI, for example, is just summation of all of these outputs times the weights. So it is UIL times ZL over all of these nodes. And ZI is when a nonlinear function applied to AI. This function in perceptron was a sine function, but here usually we have a smooth version of sine function. For example, this is our function. Delta I is 1 over 1 plus e to the power of minus a. So it looks like sine, but it's a smooth. So you can take derivative of this. It's differentiable. So is it clear so far? Any question? Okay, so this is the structure. Now I need to take derivative of, say, y minus y hat is my objective function, and I need to take derivative of e with respect to one of these weights. Say, for example, I would like to take derivative with respect to UIL. Okay. So backpropagation is basically a chain rule, You just apply chain rule in a wise way, and you eventually can find this derivative. So to take derivative of e with respect to UIL, I can take derivative of a with respect to AI, and then take derivative of AI with respect to UIL. Okay, so it's just chain rule. I apply chain rule here. So objective function with respect to this weight is objective function with respect to this variable, and then this variable with respect to weight. Okay. Okay, what's the derivative of AI with respect to UIL? Sorry? It is ZL. Yes. Because, see, AI is just this summation. If I take derivative of AI with respect to this UIL, it's going to be ZL. So in other words, this derivative means that I would like to perturb this weight, how much the whole basically quantity of this AI, how does this change if I perturb UIL a little bit? Okay, so this is ZL. What about this one? What's the derivative of E with respect to AI? Do we know this quantity? It's not clear what that quantity is. So I just call it delta I. But this delta I, which is derivative of E with respect to AI, I apply chain rule to this part again. So derivative of E with respect to AI, I write it as derivative of E with respect to AJ times derivative of AJ with respect to AI. Okay? So I apply chain rule again. But there's something wrong here in this formula. I have to make a small, modify this a little bit to make it correct. What's wrong here? You know, just don't forget the meaning of this derivative. I'm taking derivative of this quantity with respect to AI. Means I'm perturbing AI a little bit. Okay, I change AI a little bit. I would like to know how E has been changed. Basically, this chain rule tell me that, okay, you want to know the change of E when you perturb AI. When you perturb AI, actually, you change AJ, right? And when you change AJ, and also you change AI, I mean, afterward. But when I change AI, you know, I know that when I change AI, I change AJ. But there are many of them here, right? When I change AI, I change this AJ, I change this AJ, I change this AJ, I change all AJ of all of these nodes. Basically, to be correct, you need a summation here. A summation over all nodes of J. Because this change, I mean, if you perturb AI, the value of all of this AJ will be changed, you know. You have to take summation of all of these changes if you want to take care of this change. Okay, is it clear? So I have the derivative of E with respect to AJ. So we call derivative of E with respect to AI delta I. Now I have derivative of E with respect to AJ. I just call it delta J. And then I have derivative of AJ with respect to AI. AJ with respect to AI. Do we know this value? Sorry? Derivative of AJ with respect to AI is, sorry? Is it UJI? If it was with respect to ZI, you were right. It was UJI. But with respect to AI. Okay, so actually, in fact, we need to apply chain rule again, you know. So you said that it's UJI. It is UJI if it's derivative with respect to ZI, but it's not. So, but I can write it this way. I can write it its derivative of AJ with respect to ZI times derivative of ZI with respect to AI. And derivative of AJ with respect to ZI is UJI. What about ZI with respect to AI? It's derivative of sigma because ZI is just sigma AI, right? So this is derivative of, you know, it's sigma prime of AI, right? Okay, so let's put all of these things together. I wanted to find the derivative of my objective function with respect to one of the weight, and it turned out that it is delta I times ZL. So if you want to take derivative with UIL, it is ZL times delta I. But delta I itself is summation over J of delta J times this quantity, which is UJI times derivative of sigma AI. Okay. In fact, I can even take this out of this summation because, you know, it has nothing to do with this index. So I can write delta I to be sigma prime AI summation over J of delta J UJI. So we want to take this derivative with respect to weight, I mean one of the weights, UIL. So you need this quantity, which we don't know what this quantity is. We need this quantity, delta I times ZL. ZL we know, right? Okay. But delta I itself is sigma prime of AI. This is a noun value, right? Sigma is a noun function. I know the value of A, so I can compute the derivative of sigma at point AI times summation over J of this unknown quantity again. So if I want to take derivative of output with respect to this weight, it depends on a quantity which I call it delta I. Delta I itself depends on a quantity of the next layer, which I call it delta J. So with the same argument, I can show that this delta J depends on delta K. So each of these delta depends on the delta of the next layer, right? So what would happen if I just go up to the last layer? In the last layer, for simplicity here, we assume that I have only one node. Say this is layer K. You know, layer K just comes after some of these layers. It's output layer. Layer K, I have output, which is y hat. And I have some input. And it should come to, you know, a node similar to all nodes that we had so far. For simplicity, I assume that this node is a node that output and inputs are the same. You can always do that, right? Say, for example, this is your real output node. And y hat, just put another node after that that takes the input and get the output identical to the input. Okay? So if I want to compute delta K, delta K is what? Is derivative of E with respect to AK, right? So it is derivative of E with respect to AK, but I assume, you know, there is only one input here and one output here, so this summation would be exactly the same as this one. I mean, AK basically would be just Y hat because of this assumption that I made. Can I compute the derivative of this objective function with respect to Y hat? The objective function was just Y minus Y hat. So I have derivative of Y minus Y hat with respect to Y hat. Which is 2, in fact, negative 2 Y minus Y hat. So we can compute this, right? For the last layer, I can compute this value, the value of delta. So if I can compute the value of delta for last layer, and I know this delta of this layer depends on the delta of this layer depends on the delta of this layer. You know, each layer, the delta depends on the delta of the next layer. I can go up to the last layer when I can compute delta for. Then I get back, you know, having the delta of the last layer, I can compute the delta of the previous layer, the previous layer, the previous layer. So basically, I backpropagate and compute the delta of all of these layers. When I know the delta of all these layers, I can compute this quantity. You know, and these are basically main formula that I need to know. This formula, this one, and this one. So that's how backpropagation works. You know, you have n data point. You start with the first data point. You initialize your network with some weight. You know, I just randomly select some weights for my network, and I feed the network with the first data point. When I feed the network with the first data point, I can compute all of these values. So these values randomly have been selected. I can compute all of A's. I can compute all of Z's. I can compute Y hat based on the initial value, right? Now, knowing all of these initial values, I can compute delta K for the last layer. I know what the true Y for the first point is. I know the Y hat that my network generates. So I can compute, basically, I can compute delta K. Having delta K, I can put it in this formula. You know, this is a noun. I can put it in this formula, find the delta for the previous layer. Find the delta for the previous, find the delta of all of the layers up to the first layer. Having all of this delta, multiply this delta to any Z, you can compute corresponding weight. Okay, I mean derivative of that weight. So basically you can compute, when you initialize your network and feed it with one data point, you can compute this derivative for all of the weights. Having this derivative for all of the weights, you can basically do gradient descent. You know, I can say, okay, I have new weight, new update would be the old weight minus some learning rate times this derivative. Okay, this is, you know, I summarized the algorithm of backpropagation now. So you're going to apply an input vector x to network to find the value of all the hidden and output units. You know, you can find all of these values. You can find the value of y hat, the output unit, and these values. Okay. So we can evaluate lambda k for the last layer, which is this or 2 times of this. It doesn't matter, you know. Just scale your derivative with a factor. It doesn't matter. It doesn't change the direction. Then you have 2 essential formula. One of the formula is this that allows you to compute the delta for the previous layer, given the delta of this layer. And you have this formula which led you to compute the derivative of error with respect to a given weight when you know the corresponding delta and the corresponding z. So having this derivative for all weights, you can apply gradient descent. Okay. So that was for the first data point. I do this for the second data point. I do it for the third data point up to the last one. And I get back. I repeat this process many times until it converges. Okay? So that's basically backpropagation. Any question? So as you can see, it's gradient descent. As usual, gradient descent. There is no guarantee that we're going to find the global minimum. We are going to find a local mean of the function. So one of the reasons that neural network was out of favor for a while was this problem, that backpropagation finds a local, basically local minima of the objective function and not global minimum. It's not a problem anymore. You know, there is theoretical work recently which shows when you have very high dimensional data, local mean is not really that bad. You know, there are many local means that are as good as each other. You know, it doesn't matter if you get stuck in one of the local means. In fact, in some cases, you may benefit from local mean. We're gonna talk about model selection just right after we finish with backpropagation. And you are going to see that in model selection, you have to avoid overfitting, and this local mean in some cases help you to avoid overfitting. Okay? So that was one particular structure of neural network, which is called feed-forward neural network. That's the most dominant form of neural network. There are other types of neural network, convolutional neural network, and recurrent neural network, and recursive neural network. The most dominant one is this feed-forward neural network. In this course, we are going to mention convolutional neural network as well, but not RNN and not recursive neural network. So if there is no question, I'm going to start talking about model selection and overfitting, but then we get back to neural network again. Okay. Any type of learning, you have a problem which is called overfitting and underfitting. You know, let me show you this. Forget about classification for the moment. You know, I give you set of points and ask you to fit a function to those points. That could be a function. This also could be a function. This is also a function. Which one is better among these three? Sorry? Second one? Why the second one is better? How do you know that the second one is better? Right. So it's a good point. If you want to learn all of these data exactly, the last one is the best one. But if you want to find the overall pattern of the data, the second one maybe is the best one. Okay? Why do we want to learn the overall pattern rather than learning all points? For new points, right? Because if I want to be able to predict new points, I have to learn the overall pattern, not all of the data point one by one. Because it's not, you know, when I give you the data point for data for n points, I have given you the value for this particular endpoint. There is no process of learning here. You already know that. If there is any learning involved here, means learning something new. What's going to happen in a new data point, not the data points that you have already seen. Okay, if you go for this third one, which is basically learning all of these data points, you have overfitted your model. You know, this is called overfitting. Overfitting means that you learned all of these examples exactly, but you can't generalize. If I show you a new point, you can't do that. Okay? And it's not just for, you know, function estimation. Even in our daily life, we have this issue, you know. I have students, you give them a paper to read, and they have like 5 types of markers, red and blue and green, and they come back to you and the paper is color coded, you know, this sentence is red, this sentence is green, this sentence is, and each of them has a meaning. And this type of a student get 100 in all of the exams and A+ GPA, but usually they are not innovative, you know. Usually you can't expect to get much out of, you know, in terms of innovation, new idea, because this is overfitting. You know, you read something and you want to learn all of the single, you know, details of this subject. So there is no room to learn anything new. It's not just about, you know, an example. You know, I tell you, what's the difference between blackboard and whiteboard? And you can tell me, okay, blackboard is black, whiteboard is white. So I can make distinction between blackboard and whiteboard. But if I have a set of examples, you know, 10 blackboard and 10 whiteboard, and I ask you, what's the difference between blackboard and whiteboard? And you tell me, okay, blackboards are those that are, you know, the length is like 2 meters, and the height is 1 meter, and the length, I mean, is 1.5, and the thickness is this. And you have n of them. You give me n different numbers, n different thickness, n different widths and heights, and so on. And you do the same thing for whiteboards. You know, give me so much detail of everything. I can do perfect for any whiteboard and blackboard in this data set. But if you show me a new blackboard, which is not in this data set, I cannot do that, you know, because I haven't seen, you know, this exact length. I haven't seen this exact thickness in the data set. So I get confused. Very small amount of data, I can do that. It's black, that one is white. Fine. You know, that's the common pattern in these two, to make distinction between these two. So basically, when we are learning a model, we have to make sure that we are learning the right model. You know, we don't overfit the data. There's another thing which is called underfitting, and underfitting in this case, for example, means you learn this function, you learn linear function, okay, which is pretty far from the true reality. So in this case, I'm trying to fit a polynomial to this data, and this is a polynomial of degree 1, this is a polynomial of degree 2, and it's a polynomial of degree, say for example, n minus 1. You have n point. If you fit a polynomial of degree n minus 1, You can go through all of these points, right? So say this is the degree of polynomial x, and y is my error, my empirical error. You know, what I predict compared to the true value. For any model, you know, you can have a curve of this form. If I choose a polynomial degree 1, I'm pretty far, I have a huge error. Then I choose a polynomial of degree 2, I have some error. Then I choose a polynomial of degree 3, 4, 5. At some point, I can go through all of these. So at some point, you know, it basically would be even 0. So I can continue the process until I have no error. Which we said is not a good thing, you know. It's not a good thing not having any error. It's overfitting. That's what's going to happen on your training set. On new data points, say on test set, this is the pattern that you're going to see. With polynomial degree 1, you have error. With polynomial degree 2, you have less error. With polynomial degree 3, on training set, you have less error. On test set, you have more error. So at some point, they start to increase. Means this is optimum. You know, at some point, you can't predict well if you give more details to the model. It's enough. You shouldn't train it more. You shouldn't give more details to the model. It's enough to learn the general pattern. And this is the optimum model. Before this is underfitting. After this is overfitting. And we have to avoid overfitting. We have to avoid underfitting. Basically, we have to find the right model. This is called model selection. Okay? And there are many different ways for model selection. For any type of model, there are some general rules, general methods to find the right model, including neural network, including perceptron, including, you know, any other method that we have learned so far and we are going to learn after this. This is general. You know, it can overfit, it can underfit, and you have to find the right model. So in this example, that was the degree of polynomial. But in general, this is complexity. So each model, you can define complexity for each model. The more complex model fit the data better, you know. They have ability to fit the data better. This is in the family of polynomials. This line is basically a model with low complexity. Polynomial has higher complexity, cubic, and so on. You know, each time you add to the complexity, means this model has more flexibility, you know. For neural network, you know, you have a neural network with one set of layers compared with a network with two set of layers. Two set of layers is more complex than one. Having more nodes means that the model is more complex. Okay? So in general, we are going to learn about model selection, and then we will see how it can be applied to some of the techniques that we have learned so far and the techniques that we are going to learn after that. So that was basically the example that I gave you on the board. When you have some data points, this is underfitting, this is the right model, and this is overfitting. And we need to avoid underfitting, and we need to avoid overfitting. So basically, this is our question. More formally, how can we choose a good classifier, in general, a good model? You know, and it's not just about classifier, about regression, anything, any type of learning that you want to do has this problem. So in terms of classification, we would like to have a classifier H that has has minimum true error. Remember what was the true error? True error was the probability that h is not equal to y. Probability. We can't compute this probability. We estimate it. Right? We estimate it. We can't compute the probability exactly. We estimate it through the training set. But our estimation, our empirical error, our estimation on truth, on training set is always an underestimate of this true error. So it's always biased downward. It's not a good estimation in many cases. So this is what we compute. This is empirical error. That's not the true error. You know, if you can minimize the true error, fine. But we can't. We minimize usually this empirical error. And empirical error can be problematic. It's not always a good estimation of the true error. Okay? So to study this problem more carefully, let me remind you of a couple of concepts. You know the concept of bias, you know the concept of variance, and you know the concept of mean square error. So suppose that f is underlying function, is a true function, and f hat is basically the function that we estimate. What really we are interested in is minimizing this. You know, we want the distance between true f and estimated f to be minimum. Okay? We have this concept, bias, the distance between f and expectation of the model that we have computed. And we have the variance, which is, you know, how stable or how wiggly is the estimation that we have. In this example, for example, this model has high bias, but low variance. You know, if I estimate a line, a linear function here, 10 times, take the average of them, it doesn't change that much. So this is not going to be big, you know. The difference between estimation and the average of all of this estimation is not big. It's low variance, okay? But it's high biased. The average of estimation, which is this line, is far from the reality. So it has high bias, but it's low variance. But this function, this wiggly function, it has very high variance. Because each time that I'm estimating this f, I get something different, you know. There are many different ways to go through all of these data points, you know. I can do it in many different ways. Each time I get a new function, new estimation. So the average of all of this estimation compared to the estimation that I'm making now could be pretty far. So it's high variance, but it's low bias. You know, it's always a trade-off between variance and bias. You know, we can say that variance plus bias square is basically mean square error. So fix mean square error, you change the variance, you decrease the bias, variance get increased, and vice versa. There's always this trade-off between this quantity. And there's always these phenomena that we explain on the board, that empirical error or training error always decreases when you change the complexity of the model. More complex model, less training error, less empirical error on training set, but that's not the case for test sample, for new data points. So this is the area of low bias and high variance, you know. These type of models are high variance, but they have low bias. And this is the area of high bias, but low variance. So, and basically in this two corners, we want to avoid all of these two extreme. We want to find a point, a model with the right complexity. That's the art of model selection or complexity control. Okay. Okay. So there are different ways for model selection and for complexity control. One way for complexity control is estimate the true error rate. So I told you that the probability that hx is not equal to y, that's true error, which we estimated through some empirical estimation. If you can minimize the true error, you're fine. You know, the problem starts when we approximate it by empirical error. So the first approach to model selection is somehow estimate the true error. Not just empirical errors. You know, we fix empirical error in a way that this empirical error is a representative of the true error. I may not add a factor to this, subtract a factor to this, do something about it, you know. So the first approach is to estimate the true error. To estimate the true error, there are two major approaches under estimating the true error. One of them is cross-validation that we are going to learn about in details in this course. It's very simple, very general technique for model selection. It's called cross-validation. The other one is computing error bound. We're going to see just a little bit of flavor of this type of computing. You know, there's a usually, you know, this approach is that there are many inequalities in probability, and we use these inequalities to put a bound on the true error. You know, we claim that the true error cannot be less than this, cannot be more than this. This is theoretically very interesting, very elegant techniques. In practice, usually this type of bounds are loose bounds. They are far from true error. You know, it's a bound of error. And, you know, your true error is here. This bound is here. It tells you that it cannot be more than this. This is true. And you can, I mean, theoretically, you can prove it. But it's loose in a sense that it's far from here. It's worst case scenario, you know. Worst case, it's as bad as this. Cannot be more than, cannot be worse than this. But in practice, it's way better than this. You know, semi-supervised learning, everyone uses semi-supervised learning, a good result. Theoretically, you can prove that for the bound of semi-supervised learning, theoretically, you can prove that using unlabeled data doesn't improve the bound, you know. It means that semi-supervised learning is useless. I mean, if you just use your labeled data, the bound is better than using unlabeled data and labeled data together. Theoretically, you can show that. But in practice, semi-supervised learning is useful because this bound is very loose. It's here. And reality is here. So there are many elegant techniques, interesting theoretical to study. May not be that useful in practice, but we're going to see a little bit of this. We're going to see this in detail. And there's also regularization. Regularization means adding you know, a penalty function to your cost function when you optimize it. And we just see a little bit of this, you know, for neural network, for example, we see weight decay, how to add, you know, L2 norm to this and why we add that at this level. We don't go through the detail of that. Okay, let's start with cross-validation. Cross-validation maybe is the simplest way to do model selection. It's quite easy, you know, you're going to leave some of the data out in the time of training. So I have this amount of data. I divide it in two parts. I just use this part for training, and I don't use this part in the training. I call this part validation set. Okay? So far, in training, we used to minimize the objective function. And the objective function was, for example, the difference between true value and estimated value over all points on the training set. So if I had n point in the training set, that was my empirical error. What I'm going to do now is to divide my training set. Say this is n data point. I'm going to divide my training set, put m of them here, and L of them here. And I'm going to use only this part in training. But when I want to measure the error, I use this part to measure the error. In this example, in this example that we have, I'm going to use m points to learn the parameters of a linear function. When I computed the linear function, I want to measure the error of the linear function. I use this point that hasn't been used for training the model. So when I compute this over I up to L of these points. Then I go for quadratic. Then I go for cubic, and so on. So do you remember that that was the curve for training set for the points that we have observed? But that was the curve for the points that we haven't observed. So I'm measuring the points that I haven't observed. I'm measuring the error for the points that I haven't observed, right? So it's not going to decrease all the time. It's going to start increasing at some point. And that's my right model. This is the most, this is vanilla version of cross-validation. It's a very simple version of cross-validation. You put a part of the data aside. You don't use it in training, but you use it when you want to measure the error. Okay? So we basically measure C over all the data points in set V, validation set. So we calculate the error according to validation set, not training set. So one of the bad things about this is that it's gonna basically, you're going to lose a part of data that you have for training. So data usually is quite valuable. I have n data point for training. I have only 100 data points, and you tell me that put aside 30 of them. You just use 70 of them. So it's going to affect my estimation. My estimation is not going to be as good as estimation using 100 data points, because I'm losing some of the data that I had for training. Okay. One way around this is k-fold cross-validation. Okay. In k-fold cross-validation, this is all of the data that I have. Okay? And I'm going to divide this data to k parts. Then I'm going to put this part aside and train everything based on this 4 part, and then use this part to estimate the model. Exactly what we did before. But I'm going to do the same process again, but this time I'm going to put this part of the data aside, and I'm going to use these 4 parts to train the model. I'm going to do it again. This time I don't use this part, I use the other parts. And I use, I have, say for example here, I have k parts in the data. I repeat this process k times, and in each time I put 1 part aside. I learn k minus 1 part of the data to train the data. Somehow I get around this problem that a part of data hasn't been used in training. You know, basically I use all of my data points in training. But in each part of the training, you know, I put one portion of the data aside. So this is called k-fold cross-validation. And in k-fold cross-validation, you divide your data to k chunk, and in iteration you remove chunk k from the data, compute the classifier from the rest of the data. So you remove this part, you calculate it using the rest, or you remove this part, you calculate using the rest. And so when you compute the error with the chunk that you haven't used in your training. But then you take average of all of these errors. You know, I had an error when I applied this part, and I trained the model using this and applied this part to the model. I trained the model using this and applied this. So I have k scenario the same. So I take the average of all of these k's. That would be my error. Okay. So basically, I learn a linear function, but I go through this 10 or k folds of learning, and then second and third, and I mean quadratic and so on, and then I decide which one is the best one. So somehow we resolve the problem that a part of data is not going to be used. But there's another problem here. Can you see that? Sorry?
Yeah, with the smaller size.
What is a small? I mean, this is small? I mean, no, you can take a large part. Doesn't matter. You're going to choose it. Yes?
Are you going to do K models? Then you have K different models when you do that?
No, you don't have k different models. You are going to have one model.
Train K different models. Or K different trained, like, with the same model, but trained on K different data sets. So you have an estimate for, like, I guess, like, which one are you going to use to classify your data?
I mean, at the end, you are going to have one model, not k model. But to find that one model, you need to repeat the process of learning k times. Right? So when I had n data point, I was able to feed a line to this n data point. Say, for example, list square. Right? Now I have to do a list square here, 10 times. Take the error and report that the error for linear model is this. Then go for quadratic. And so for each complexity, I need to do the training k times. Okay? So that's the drawback here, that if training is computationally intensive, in many cases it is the case. So you can't do that, you know. Say, for example, for many of the neural network models, you have high performance computer and you have GPU and you have CPU, and still you have wait 1 week for training, you know. You can afford k-fold cross-validation, you know, and, you know, to come up with the right, say, for example, a structure. It doesn't make sense. So you have to do something different. But if the training is not that expensive, it's a very good technique, you know, you can do it. And you do logistic regression, it's fine, you know, you can do that. You learn, you know, something which is not that expensive, you can do that. Quite often you see in papers when they report their experiments that, you know, we use 10-fold cross-validation. 10 is quite often, quite common. They say we have used 10-fold cross-validation for you know, this experiment. But some people say that k could be anything, but you see papers, they say that, you know, we have used like 6-fold cross-validation to the. Do you know why they do that? Instead of 10, why they use 6? 12? Sorry? Yeah, so why instead of 10 they would say that we have used 11-fold cross-validation?
Parallel processing and then have 6 maybe cores of it.
Well, any of these could be the reason, but usually that's because they're cheating. You know, when you see this type of numbers, get suspicious. That why don't you use 10-fold cross-validation? Because usually they torture the data until it provides good result, you know, and they provide the best result for the paper. So they go with 10, oh, no, they're not that good. Let's do 7, 8. Okay, 6 is fine. So let's report that, you know, 6-fold cross-validation, we beat everyone else in the world. Yes?
In the assignment, we did like PCA and then classifier. So when we're doing cross-validation, do you do cross-validation on your entire, like from input data to output data, or would you do PCA first and then cross-validate on just the classification?
You can do PCA first and then do cross-validation afterward. Actually, it makes more sense to do it this way.
So your error rate doesn't include your remapping the data to a new?
No.
And it doesn't
You learn your feature and then you do cross-validation afterward. You can do the other way around, you know, it depends. But in this particular example, you know, it's fine to learn the subspace for the whole data point that you have and then do cross-validation.
But isn't the subspace also an approximation from like the parameters you learned in your PCA are an estimate of the true parameters, right? That you would get if you could see all the data.
We are talking about two different models. We have, you know, a classifier that we want to learn, and we make some assumption about the data that this data is close to subspace. So you can separate these two parts. For the first assumption, the data is close to subspace. You apply PCA to whole data, and then go and learn your learn your classifier based on this assumption that you have already made. You don't need to mix these two. You can, if you want. Sorry. You can, but you don't need to. I mean, most likely, you know, the subspace that you are going to find using all of these n data points is a better subspace than, you know, a part of that. Okay. Any question here for k-fold cross-validation? Okay. So there is one variation of k-fold cross-validation, which is called leave one out cross-validation. And leave one out cross-validation, you know, you have n data points, assume that you have n folds. That's leave one out. So basically, you have to train your model n times. So I put the last data point aside. I learned the model with n minus 1 data points, but I compute the error on the last one that I haven't used. I put point n minus 1 aside. I learned the model using all of the n minus 1 remaining point, compute the error on this one, and so on. So it's n-fold cross-validation basically for n data points. It's called leave one out. Leave one out, you know, could be quite extensive when algorithm is hard, and I mean algorithm is computationally intensive and so on, and it has high variance as an estimator. But in some cases, actually, you can get around that. You're going to see this in one of your assignments, that if the model is linear, you can avoid computing n different models. You can learn model once, but compute leave one out error based on one computation. You can do that. Okay, there's a way to get around that. Any question here? Okay. So we are not completely done with neural networks. So now that we learned about cross-validation, I'm going to you know, talk about another model, another type of neural network. It's called radial basis neural network. We are going to learn about radial basis functions neural network, RBF. Then we will see regularization for neural network, like weight decay. And then we will see some more theoretical, basically concept that how we can control the complexity, how we can compute a bound for RBF, for example. Okay, so have in mind sort of road path what we are going to learn in this lecture and next lecture and next couple of lectures. Okay, so radial basis neural network have this structure. It's a sort of neural network with one hidden layer, only one layer. You have input, you have d-dimensional input, and you have a layer of m nodes. These nodes are not perceptron, these are just nonlinear functions. Okay? So basically, this phi is a nonlinear function applied to point x. Point x is d-dimensional, you know. It observes point x and this d-dimensional and apply a nonlinear function to it and has an output. And you have m of these nonlinear functions. And then in the last layer, you always, you know, RBF always has this one layer of hidden. Doesn't have more than that. And you have some weights here. Here, actually, the output would be similar to perceptron, which is a weighted sum of these inputs, these outputs. Okay? The weighted sum will appear here in the output. Okay. There is no weight here. In the first layer, we don't have, from input layer to this hidden layer, we don't have any weight. From hidden layer to output, we do have a set of weights. And as usual, we will need to learn these weights, you know, because this is the parameter of the model. We need to learn these weights. Okay? So this is the structure, and now we have to see how we can learn these weights. Okay, so I have this x1 to xd, and I have like phi 1 to phi m, and I have output which is y1 to yk, and I have weight here. I don't have any weight here. Okay? So what's going to happen is that, you know, I have d-dimensional data, and this d-dimensional data will be applied here. So basically, like phi 1 of x will be computed, phi 2 of x will be computed. And these are outputs. And the final output is a weighted sum. You know, for example, this one is like W11 times phi 1 x1. So this is x1. Or in general, x. Plus W 21 phi 2 plus Wm1 phi m. This is going to be my y hat at point x. Okay, so if it's yx1, for example, that's going to be y1. Okay, we need to basically find this set of weights here. So any idea, any suggestion? Any suggestion to do this? Okay, let me write it this way. I have a function, I have a matrix X. Suppose that I have n data points. So I have a matrix X, and such that each column of this matrix is one of the data points, and I have n of them. So basically, this is D by n matrix. This is x11. This is xd1, and this is x1n, and this is xdn. So this column is vector of x1, and this column is vector of xn. I define a matrix phi of all of these values that this function, or all of these m functions, can compute for my all of n data points. My first data point will be applied to phi 1 and has a value, will be applied to phi m and has a value. So in total, I have m times n values, when phi 1 is applied to x1, and when phi m is applied to x1, when phi 1 applied to xn, and when phi m applied to xn. There's m times n values. I put it in a matrix of this form. Okay? And I have y as a matrix. And this matrix is, I have basically k by n values, because this is, as you see, it's k dimensional. So for given point, for any point, I have y1 to yk, and I have n of them. Right? And I can put all of my weights in a matrix. So how many weights do I have? I have m nodes here, and I have k nodes here. So it's in matrix m by k, right? So basically, it's a matrix m by k. So this is W 1 up to WM1 and W1K, WMK. Okay? So I can put all of my weights here. So now I can basically show this output using matrix notation. I can say that y, my output, is what? Is this matrix W times phi. Right? So W transpose times phi. Am I right in terms of dimension? This is m by n. W is m by k, so it's going to be k by m. So y is k by n. Yeah, that's right. So y is just W transpose phi. So I can write my output in terms of this matrix multiplication. And this W is unknown. Y is known and phi is known, right? Phi is a function, a nonlinear function that you choose. It's called your basis function. It's called radial basis function. you choose your basis. So I can have these values. You know, I know my x. I choose my function phi. I apply phi to x. I fill up this matrix. And I have my output. I have my input. The only thing that I don't have is w. Now I want to compute this w. How can I do this? Least square. You know, I can compute. I can minimize this. Okay? And find w. So should we do gradient descent again? Take derivative of this and do gradient descent, update w? Yes? No? Is it good if I do gradient descent here? Do I need to do gradient descent here? Yeah, it's just least square. It has closed form solution. You don't need to do gradient descent. You know, you can find, in closed form, you can tell me what the solution is, you know. Sorry?
Is phi transfer times phi
Inverse.
inverse and times phi transfer times 1?
Yeah. Yes, basically, you know, this cost function, you know, this norm is just trace of y minus w transpose phi transpose y minus w transpose phi. If you take derivative of this with respect to w, you know, this is basically, you know, you have a quadratic form. For the first one, you have a quadratic form. For the second term, and you have phi w, you have phi transpose w y, and you have y transpose w transpose phi. And you have trace of this. Now you have to take derivative here. You have 4 trace here. You have to take derivative of this trace with respect to w. This is 0. Derivative of trace of phi transpose w, w transpose phi, it's quadratic with respect to w. And it's just 2 phi transpose w. And this is, I mean, trace of this with respect to w, if you take derivative, it's just y phi transpose. This is also y phi transpose. And then you set it to 0. So phi transpose w is y phi transpose. So w is phi transpose inverse y phi transpose. I think I made a mistake here. It should be, I think, y phi transpose y. It should be phi transpose y. Let me see, y is k by n. Phi transpose is no, we made a mistake in this transpose here. Phi, it's y phi transpose. Okay, sorry, it's y transpose phi. Okay, so it's phi Y transpose. So this is going to be n by k. Yeah, this n by k. Then phi is m by n. Phi transpose is m by m, and the inverse is also m by m. So m by m, m by n, n by k, it's m by k, and w is m by k. Yes, that's correct. So that's the solution, basically. So solution is phi transpose inverse, phi y transpose. So we can solve it in closed form. Any question? Okay, see you on Thursday.